Hi everyone. Today we're going to talk about the final section we're covering in chapter 11, which is 11.6, and it's going to be discussing the Bessel equation and the Bessel functions that arise from it. So the Bessel functions are some of the most important functions in applied mathematics. And in the course of defining the Bessel function, we're also going to take a look at the gamma function as well. To begin with, the Bessel equation and the Bessel functions that are the solutions to the Bessel equation show up in the analysis of the propagation of waves, which is one of the core sort of ideas that we need in most of the physical sciences and in quite a number of applications in applied mathematics broadly and the implementation as well. And Bessel functions turn up to be useful not only in physical applications but in approximation theory because they're going to provide another family of orthogonal functions that we can use to do analysis or approximation in a defined setting. So what is the Bessel equation? So equation of the order x squared y prime prime plus xy prime plus x squared minus alpha squared y is equal to 0 is called the Bessel equation. And the alpha that's in there is a parameter. So alpha is a parameter. And it's important enough for fixing the setup that we're in that the Bessel equation itself is called the Bessel equation of order alpha. Now it's typical to introduce this in the broadest level of generality, and Bessel's equation actually works where alpha could be any complex constant. We're going to be focusing on the case where alpha is a non-negative real number, but it's important to note that the techniques that we're working on here actually give rise to a whole family of functions in the complex domain as well. It's pretty easy to see just by looking at this equation that it satisfies the assumptions that it has a regular point at 0. So this is in that family of functions that have a regular singular point at 0. And this particular function has p of x equal to 1 and q of x equal to x squared minus alpha squared. And so p of 0 is going to be 1 and q of 0 is going to be minus alpha squared. And what we're going to see then is that the initial equation is r times r minus 1 plus r minus alpha squared, which turns out to factor as r squared minus alpha squared, which is r plus alpha, and r minus alpha. And that means that the roots of this equation are going to be r1 is alpha and r2 is minus alpha. And so this equation, as can be predicted from the fact that it has the right form, is one that is amenable to solution using Frobenius series. So as long as two alpha is not an integer, which is really just saying that alpha minus negative alpha is not an integer, then we can assume the solutions have the form y is equal to x to the alpha times the sum from n equals 0 to infinity of an x to the n, and y2 is x to the minus alpha, sum from n equals 0 to infinity bn x to the n, as is typical of our Frobenius series approach. So the way that we solve Frobenius problems is we always take the general equation with x to the r, and then we get the recursion, and then when we need to, we plug in r is equal to alpha. So that means that we're going to be looking at the general solution y is equal to x to the r times the sum from n equals 0 to infinity of an x to the n. And we're going to use this to find the recurrence relation. So you get the following recursion, and from there, once you collapse the series together and pull off the first two terms of the series on the left, then you end up with the actual coefficient recursion, n plus r squared minus alpha squared an is equal to an minus 2. Okay, where the n equals 0 and n equals 1 terms end up just recovering the index equation that you started with. Okay, so again, this is under the assumption that alpha, or that 2 alpha, is not equal to an integer. And from here, then, of course, you could just write down that an is equal to 1 over n plus r squared minus alpha squared, an minus 2, the negative on top. Now, if you put in the r is equal to alpha, that we know must be one of the values of r for which this recurrence relation generates a solution, then the recurrence relation turns into an is equal to minus 1 over n plus alpha squared minus alpha an minus 2. That's pretty obvious. And if you put that in and you cancel everything out by subtracting the alpha squared that's out here from the alpha squared that pops up right here, what you're going to end up with is a recursion that looks like an is equal to minus 1 over n times 2 alpha plus n, an minus 2. So this is the general recursion that we get for Bessel functions. And this is for any alpha. The first thing that we should note is that only even terms will appear in the series that we get as solutions to this. And it's obvious why, because the gap that you get, an and an minus 2, that gap is too wide. So we know that a naught is not equal to 0, but pulling off the 2 terms in the front of the series is going to give us an expression in terms of a1. And that means a1 will be 0, and a1 will force a3 to be 0 because of this gap between an and an minus 2, which is to say a1 determines what a3 is, and a3 determines what a5 is, and so on. And so since a1 was equal to 0, that means all of the odd terms must be equal to 0. So these functions are even, which means they're going to be symmetric about the y-axis. Okay, so algebraically we get this. What do we do from here? Well, we just use the typical trick, right? Which is that a1 forces a3 to be equal to 0, and a3 forces a5 to be equal to 0, and so on. And then for the other family, we have that a2 is equal to minus 1 over 2 times 2 alpha. Yeah, I love 2's and alphas mixed together. 2 alpha plus 2 times a0. And what's going to happen here, and this is the thing that we should be watching for in the pattern, is that as I on this side, I'm going to get things look like 2, 4, 6, 8, and so on are going to pile up because of this n right here, right? And then this is a 2 alpha plus n, so we're going to get 2 alpha plus 2 times 2 alpha plus 4, and so on as we keep going. So what do I mean by that? Well, if you look specifically, say, at a4, you have minus 1 over 4 times 2 alpha plus 4 times a2, except I know a2, so I can write minus 1 over 2 times 4 times 2 alpha plus 2 times 2 alpha plus 4 times a naught, and then there's another negative 1 on top, so that this all becomes a minus 1 squared. And then that general pattern continues. Since the terms are all even, we can re-index, and so the formula that we're going to get out when I look at the final pattern is going to look something like a2k is equal to minus 1 to the k. That's the alternation. And on the bottom, we start multiplying at 2, and we go up until we get to 2k. That's the n. And then we have more terms that involve the 2 alpha. So there's 2 alpha plus 2, and we multiply those until we get up to 2 alpha plus 2k. And then all of that is times a naught. Now, this has a lot of 2's in it. That should be pretty clear. There's just 2's running all over the place. This formula for computing a2k in terms of a0 can be simplified by just pulling a whole bunch of 2's out. a2k is equal to minus 1 to the k over 2 to the 2k times k factorial times alpha plus 1 dot 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 up to alpha plus k, a naught. Now a naught generally can be chosen when we're dealing with families of solutions. And so what we've shown here is that we have a family of solutions that are dictated in this way. So what do I mean? I mean that y1 of x is equal to x to the alpha times the sum from k equals 0 to infinity of minus 1 to the k over 2 to the 2k, k factorial, alpha minus 1 or plus 1 up to alpha plus k, and all of this has an alpha naught in here. In the same way that when I was looking at the Legendre differential equation, I picked out special solutions by looking at special cases, and then those special functions turned out to be super important, I'm going to isolate the case in which this function has its most important solutions. At this point, the way I have this written down, alpha could be any non-negative constant. But I want to further restrict my attention to the case where alpha is actually an integer n. So let's assume that alpha is just n, where n is a positive integer. That corresponds to most of the applications that you see this equation used in. Then, also, I can simplify algebraically the representative solution by choosing a magic value of a naught. So there's an exercise here. So I'm going to pick a naught is equal to 1 over n factorial times 2 to the n. And if you do that, and you multiply that into the formula, you end up with this really interesting algebraic collapse that happens, which looks like this. y1 of x in this case can be written the sum from k equals 0 to infinity of minus 1 to the k over k factorial times n plus k factorial times x over 2 to the 2k plus n. And this equation right here, in the same way that those magic polynomials that solve the Legendre equation we said were super important, gave them a name, the Legendre polynomials, this function right here is so important that it gets its own name. And one of these exists for every value of n. So j n of x, which is equal to the sum from k equals 0 to infinity of minus 1 to the k over k factorial times x plus k factorial x over 2 to the 2k plus n. That particular solution to the Bessel equation of order alpha equal to n is called the Bessel function of the first kind of order n. Bessel functions are ubiquitous in applied mathematics and everywhere where applied mathematics is used. Okay, so it's one of the most important families of special functions that are running around in terms of the way they get used in application. But of course, if I say that a function is of the first kind, then it seems likely that probably there's a Bessel function of the second kind as well, and we'll get there. The first thing I'd like to show you is how these things get used when we are studying waves, right? Systems that involve waves. Why do the Bessel functions come up? And it would be useful to look at their graphs to take a look at what these Bessel functions of the first kind even look like. So on the online notes for this, I've got some Sage code. I will build a demo for Bessel functions as well eventually. But if you evaluate the Sage, you can actually look at some of the graphs for what the first couple of Bessel functions look like. The Bessel J here refers to Bessel functions of the first kind, and we're just picking different orders, so order 0, order 1, order 2, which are solutions to those respective Bessel equations. And you can see that this set of functions has properties that might be useful in studying waves. They oscillate, but they also decrease asymptotically in amplitude as we head out towards infinity. And so Bessel functions are used a lot of times to model problems where you have waves that are propagating, but the energy is dispersing radially as you head out. So that's just what they look like. So they oscillate with a certain period. They diminish in amplitude as they head out towards infinity. So now what we're going to do is we're going to try to figure out a way to take what we've written right here. That is, we've defined Jn, the Bessel functions of order n, to be this particular function right here, which has factorials in it. But what happens if the alpha from my original problem was actually not an integer? Well, factorials don't make any sense. But I want to be able to use Bessel functions when the order is not an integer order. So I'm going to have to extend what I'm doing in order to account for the non-integer case. And that means I have to introduce one of the most famous and most important special functions in all of math, which is called the gamma function. So the goal of this is I want to take an expression like n plus k factorial, and I want to turn it into something where n is not an integer. So what I'm really trying to do is come up with a way to do factorials when I don't have a number that I can multiply all integers up to. So the gamma function extends the factorials to non-integers. It just fills in the gaps between the factorials. So if you try to make a plot of what the factorials look like, well, if you put 1 into 1 factorial, you get 1. And if you put 2 into the factorial function, you get out 2. But if you put 3 into the factorial function, you get out 6. And so you end up with this function that's increasing incredibly quickly. Of course, 4 goes in and turns into 24. And what I want to do with the gamma function, one way of thinking about it, is to put a really smooth function that connects all these dots. So I want to have a function that connects all these dots in the smoothest possible way so that I can take derivatives of it, because derivatives are nice when we're doing any sort of applied math. Okay? So the question is, how do I do that? I have to come up with some function that is smooth, and when I put numbers in, factorials fall out. So I want a function that is 1, smooth, so I can take derivatives, and 2, produces factorials on integer inputs. It turns out the way we do this is with a function defined as an integral. So we're going to define the gamma function in this way. Gamma of x is equal to the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. So integral defined equations or integral defined functions are perfectly valid objects. And we can't do any better than this, really, because this integral doesn't have a closed form. In some cases, if I choose x to be an integer, you're going to have to believe me for a second here, the factorial is going to fall out. But if x isn't an integer, there is no nice form of this. And so what mathematicians and scientists have done is when they run into a function that they can't write in a nice enough way, they just name the ugly thing something nice. So gamma of x is a nice looking representation of this improper integral. Okay, so let's compute a couple of values of the gamma function and see if we can figure out what it's actually doing. So what we're going to do is we're going to start with f of 2. So what we're going to do is we're going to start with gamma of 2. So gamma of 2 is equal to the integral from 0 to infinity of t to the 2 minus 1 e to the minus t dt. This is an integral you can do with integration by parts and improper technique, so that this is going to turn out to be something like the limit as b goes to infinity of minus t e to the minus t plus the integral from 0 to 0 to b of e to the t, negative t dt. You'll get that after you do integration by parts. When you evaluate this limit, all of this stuff disappears because when you go to infinity, this part goes to 0, and at 0, that part goes to 0, so that whole term vanishes. And this turns out to be equal to 1. So gamma of 2 is equal to 1. So far, so good. I put in a 2 and I got out a 1, so maybe it takes the factorial of one number lower. Well, we could check that. Maybe we guess already that maybe we believe that gamma of n is equal to n minus 1 factorial on the basis of this very weak piece of evidence. We'd have much stronger evidence if we computed it for one more value. So let's do that. Gamma of 3 is the integral from 0 to infinity of t squared e to the minus t dt. And if you compute your partial fractions here with u equals t squared, and dv is equal to e to the minus t, then what you're going to get is, when you write down the integral of uv minus v du, is that this is the limit as b goes to infinity of minus t squared e to the minus t evaluated from 0 to b. All of that will turn into nothing just by L'Hopital's rule, plus the integral of 2 times t e to the minus t dt evaluated from 0 to b. And this dude right here, we already seen that because that's this. So that's gamma of 2. So this integral right here is gamma of 2. So this whole thing is 0 plus 2 times gamma of 2. But what's gamma of 2? Gamma of 2 is 1. So this is 2 factorial. So putting in 3 spits out 2 factorial. So if we want to show in general that this pattern holds, so if I started with 2, I got 1 factorial. If I put in 3, I get 2 factorial. I could show that that rule always holds, and that lets me do what's called induction. And so what rule do I need to hold to show that gamma produces all of the factorials? I need to show that gamma of x plus 1 is equal to x times gamma of x. So this rule right here is basically pointing to the fact that if there was an n factorial here, that this would have to be equal to n times n minus 1 factorial. So what is gamma of x plus 1? From the definition, gamma of x plus 1 is equal to the integral from 0 to infinity of t to the x plus 1 minus 1, which is just t to the x, e to the minus t dt. And I can do integration by parts with u equals t to the x and dv is equal to e to the minus t. And right here you should see that it's going to work the same way because the x came down in the derivative and we have an x minus 1 right here. V will be e to the minus t dt. When you plug that back into the equation, what you're going to get is that all of this is equal to the limit as b goes to infinity of minus t to the x e to the minus t plus x times the integral from 0 to b, this is evaluated from 0 to b, of t to the x minus 1 e to the minus t dt. But all of this right here, that's just gamma of x. So this whole thing turns into 0. So here's the x that we needed for this x right here. And this, by definition, is gamma of x. So what we've shown is that this rule holds. If I know that gamma of x plus 1 is equal to x times gamma of x, and you put in any integer you want, like say 5, gamma of 5 must be equal to 4 times gamma of 4. But gamma of 4 is equal to 3 times gamma of 3. And gamma of 3 is equal to 2 times gamma of 2. And gamma of 2, we calculated, was 1. So we have a starting point because we figured out what gamma of 2 was. And that means all of this is 4 factorial. So any integer that you put in is going to run through this process, which is an inductive process. Generally, we can use this to say that gamma of n plus 1 is equal to n factorial. So the gamma function is the function that produces factorials as outputs and then fills in the gaps in between. Okay, so that was a long-winded explanation of what the gamma function is, but we use the gamma function when we're trying to extend a formula that has factorials in it into numbers that are not integers anymore. So when we had n was an integer, we said that Jn of x was equal to the sum from k equals 0 to infinity of minus 1 to the k over k factorial times n plus k factorial. x over 2 to the k. So how do we extend this when n is an alpha and is not an integer? The whole point here is that there's an n right there that I want to get rid of. Well, I'm going to have to put a gamma in there if I want n to be something that's not an integer, because I need to fill in the functions that fall in between the gaps between the integers. So what we say is, if alpha is any non-negative constant, then j alpha of x is equal to the sum from k equals 0 to infinity of minus 1 to the k. The k factorial is still okay, but since I'm replacing n with an alpha, I can't use n plus k factorial. I have to write gamma of alpha plus k times x over 2 to the k. So this move right here, where I went from the factorial to a general gamma function, includes the case that alpha is an integer. Because if it's an integer, then the gamma function just spits out factorials. And there's one more modification that I missed here. So I've made a slight mistake, which is that because of the way the gamma function works, I had an n plus k factorial here, so I actually need to plug in one higher value. So it can't be alpha plus k. It has to be alpha plus k plus 1. Because gamma of n plus 1 was equal to n factorial. So if I want factorials to match, I have to put an extra plus 1 in there. So where are we at so far? We defined a thing called the gamma function. And the gamma function was defined in terms of an integral. So gamma of x was the integral from 0 to infinity of t to the x minus 1 e to the minus t dt. And the gamma function is the function that produces factorials according to the rule that gamma of any integer n is n minus 1 factorial. So the gamma function produces factorials when evaluated on integers. Okay. With that, we defined this really important family of functions called the Bessel functions of the first kind of order alpha, where alpha is just some non-negative constant, and we get j alpha of x is equal to the sum from k equals 0 to infinity of minus 1 to the k over k factorial gamma of alpha plus k plus 1 times x over 2 to the k. Which admittedly is sort of an atrocious looking formula, but it just comes out of the Frobenius series computation. And fortunately, you never actually have to compute this because someone put it in a computer program for you. So now the big question is, what about the second solution? So the first thing that you could note is that actually in this formula, there's nothing stopping me from just taking this exact formula right here and putting in minus alpha for the other number, right? I could go back to the beginning and I could run the recursion and I could rederive everything here, including the gamma function and making sure everything lines up. But all I have to do to get the second linearly independent solution to the Bessel equation is just take this thing and just switch this alpha into a minus alpha, which is only going to change this one thing right here. So the other solution to x squared y double prime plus xy prime plus x squared minus alpha squared y is equal to 0. Well, I should say not the other solution. I should say an other solution is just given by minus alpha of x is equal to the sum from k is equal to 0 to infinity minus 1 to the k over k factorial times gamma of minus alpha plus k plus 1 x over 2 to the k. But that's actually not usually what we use when we're working with Bessel functions. It's sort of beyond the scope of the course to tell you why, except to say that it's very useful in numerical computations to have families that are very different when you're constructing solutions to differential equations. Because If I know that J alpha is a solution and J minus alpha is a solution, then any linear combination of those two is also a solution to the differential equation. So what we know right now is that J alpha and J minus alpha are a linearly independent set of solutions. But since we know that J alpha and J minus alpha are linearly independent, then any linear combination of them is as well. And so we actually use this to define a function called y alpha of x. And this is a Bessel function of the second kind. And the particular linear combination that we use is going to look kind of weird. It's J alpha of x times the cosine of alpha pi minus J minus alpha of x over the sine of alpha pi. The reason that we define it this way is because this will actually let us compute a second solution very easily in the case where there is an integer difference between alpha and negative alpha. Okay, so this form of the solution works when 2 alpha is not an integer. And the reason that we have to set it up in this bizarre way with this linear combination, you should see here that this is a constant. You should see here that this is a constant times the first solution minus a different constant times the second solution. So this is a linear combination of J alpha and J minus alpha, which means it is itself a solution. The reason that you set it up this way is because this lets us handle the case where the alpha has the property that alpha and minus alpha differ by an integer. If alpha and minus alpha do differ by an integer, then we can actually use the formula above to say that y alpha of x is equal to the limit as alpha tends to pi of J alpha of x cosine of alpha x minus J minus alpha of x over the sine of alpha pi. So pi is not x's. So one of the most important things about Bessel functions is that we can show that Bessel functions form an orthogonal basis for a vector space of functions that have derivatives that are continuous. In order to do that, I have to tell you how to generate the orthogonal family. You might want to know why you want to do that. Well, if you're working in a regime where the space that you're working in or the physical problem that you're working in is dictated by a Bessel function, which dictates exactly how that system works, then I want to take down complicated behavior, like a function. I want to break it down into the sorts of behaviors that are possible in that system in terms of these Bessel functions. Each Bessel function models a different kind of propagating wave that is possible in the system that the Bessel equation sets up. So how do I do that? Well, the first thing to note is for any value of alpha, the Bessel function of the first kind, J alpha of x, has infinite zeros. Now, you saw a piece of the graph where the Bessel functions kind of look like this, and so you could believe that they have infinite zeros, but that's something that needs to be shown. It can be done. And once you know that, well, you can just list them in order. Now, they're infinite, but you can list them from beginning to end. So that is, you can make a list, lambda 1, lambda 2, forever, where the lambdas are the zeros of J alpha of x. So what do I mean? I mean J alpha of lambda I is equal to 0 for all I. And those zeros are specific to the parameter alpha. So in many contexts, you'll see these lambdas tagged with another letter to let you know that they are the zeros specifically for the function J alpha. So you might see something like lambda 1 alpha to say those are the zeros that go with the Bessel function of order alpha. So what that means is that we can define a slight modification of Bessel functions that look like this. I'm going to have a whole family for a fixed alpha So you fix the system. That's what you should think about the alpha. You're fixing some parameter about the physical or abstract model that you're working on that tells you that is the world I'm living in, a fixed value of alpha. For a fixed value of alpha, it turns out to be the case that you can define a family of functions j alpha lambda I x. So you take the zeros and you put them inside the argument of the function. So this is a new function. It's built out of j alpha, but it's a new function. Okay. And of course, there's going to be infinite number of these because there's one for every zero of the function. So what is this function evaluated at x is equal to 1? Well, it's 0. J alpha of lambda of I times 1 is just equal to j alpha of lambda I, which is 0. Okay, so that's a normalizing thing to make sure that all of these functions, when you put in 1, 0 falls out. So the first thing that we want to say about these functions j alpha. So we have j alpha lambda I of x. There's a whole family of these for I equals 1 to infinity, where the lambda i's are the zeros of j alpha. Okay. What matters about this is that if I let the inner product of two functions be equal to the integral of x, f of x, g of x. So this is a different inner product than the one we used before. Okay, because the x is in there. So this is actually called a weighted inner product, where the x is called the weight. It still works exactly like a dot product. You can define everything you need in terms of this. So we start with this inner product, and the reason that we choose that inner product is because with this inner product, it turns out to be the case that every j alpha of lambda ix is orthogonal to every j lambda j x, as long as I and j aren't the same. Which is to say, these Bessel functions of the first kind of order alpha that have been modified with the zeros turn out to be an orthogonal system. And not only are they an orthogonal system, but they're a basis for the space of functions with this slightly modified inner product. And so the big theorem here, the upshot of all of this, is that once you have the Bessel functions and you fix down the system that you're working in by choosing a value of alpha, that you can describe any other function in that system in terms of solutions to the Bessel functions, which you can think about taking a complicated function and breaking it down in terms of propagating waves. So the Bessel function expansion theorem says this. If f and f prime are continuous, then f of x can be expanded as a sum of Bessel functions of the first kind, where the CIs are computed with the projection formulas. F dot j alpha lambda ix over j alpha lambda ix dotted with itself times j, so the coefficients follow the same exact projection formulas we use in every other kind of linear algebra. Because the functions are orthogonal, we can use the projection formulas. So what do I care that you know about Bessel functions? So this is the takeaway. 1, that if alpha is a positive number, then the differential equation x squared y prime prime plus xy prime plus x squared minus alpha squared y is equal to 0 has a family of solutions that are linearly independent called Bessel functions of the first kind and of the second kind of order alpha. So you have a j alpha of x, and you have a y alpha of x, which is equal to j alpha of x times the cosine of alpha pi minus j minus alpha of x over the sine of alpha pi. And I want you to know that with that family of functions, for a fixed alpha, and you can think about this as fixing the physical system that you're working in, that it's the case that if the lambda i's are the zeros of J alpha, then J alpha of lambda I x is an orthogonal family, and that any f that you write down that has the property that f and f prime are continuous, you can write a Bessel function expansion for that, which is to say that f is equal to the sum from I equals 1 to infinity of ci times J alpha lambda I x. So this is a unique expansion theorem. The ci's are unique. Ci's are computed just by taking dot products. Now, I'm not going to write the formula again. I'm going to tell you it's the projection of f onto J alpha lambda I x. I'm going to do a MATLAB demo for this as well, so you can see how Bessel functions give you access to periodic functions in a way that the Legendre polynomials didn't, right? Because Legendre polynomials have the property that they grow to infinity or negative infinity as you go out, right? Polynomials blow up as you head out towards infinity. But the Bessel functions do not blow up to infinity, right? They collect on the x-axis as you go out, which means maybe this is going to give us a way to model periodic equations that the Legendre polynomials fail for. So the idea of all of this is that in a fixed physical system, I want to be able to approximate functions. The Bessel functions provide us a set of vectors that we can use to do that. Okay, so this has been a lot, and thanks for sticking with me, and I'll talk to you later.